Hello, I'm Feona Dabson from the Samuelson Organic Chemistry Lab here at Ball State University. Here at the SAM Lab, our research revolves around this one small compound, malononitrile. Malononitrile is an aliphatic nitrile used as an intermediate in synthesis, spanning from different fields from pharmaceuticals to pesticides and even organic semiconductors. It is essential for carbon-carbon bond formation, and carbon-carbon bond formation is essential because it's a key step in synthesis for organic chemistry. So our lab group works toolbox chemistry research, improving methodology so that others can benefit while taking less time and resources. Over the summer, my research consisted of retrying one of our lab members, Ariana Palmer's synthesis, tweaking certain conditions, and evaluating if reaction times could be shortened and still maintain the same or higher product yield. The first scheme was reductive alkylation of malononitrile and P-anisaldehyd. Comparing results, Palmer produced a yield of 102%, which suggests impurities. For my results, trial 1, when given the condensation reaction 2 hours, gave less percent yield and more impurities. But for trial 2, when 1 day was given for the condensation reaction, we produced adequate yield and promising purity. The second scheme consisted of the isolated product from scheme 1 and then was alkylated with the alkyl group. I spent a lot of time with this scheme. As you can see, my first 3 trials produced impurities that required purification. It seems when using acetone, a reaction time of 2 days, like Palmer, can work well, but when using a solvent like acetonitrile, the reaction can be shortened by half and produce a yield and purity that's not negatively affected. The last scheme was reductive alkylation of malononitrile with different salicyladehydes. I personally only worked with 2 different derivatives, but other members in our group, like Jamila, have worked several more derivatives that follow the same scheme and have created some novel characters. Result-wise, Ariana was only able to isolate and not reduce, but even still, her 7 days could be shortened to 3 and produce high yields and promising purity. Aside from percent yield, the main mode of assessing purity in anything made is the NMR machine. NMR, standing for nuclear magnetic resonance, is an instrument that observes and measures the spin of atomic nuclei. Basically, a huge magnet. But machines like this help us chemists determine molecular identity and structure. Here you can see a highlight of the protein NMR spectra for my 3 schemes. The location of peaks, chemical shift, let us know the different types of nuclei observed. And the splitting of peaks essentially let us know the amount of neighboring nuclei. In other words, NMR presents itself as a puzzle for us to solve. Future research underway focuses on forwarding scheme 3 for further alkylation, investigating the scope and selectivity of the reaction when put under different conditions. In the end, today we learned about malononitrile, the importance of carbon-carbon bond formation, and you took a dive into the synthesis I conducted over the summer. And finally, you kind of got a little taste of the future work that's still underway in this lab group. Thank you for watching one of the several STEM research videos here today. I'd like to thank Dr. Samuelson, Jamila, Ariana, Matt, and Isabel, who bared with me in my endless questions. And I'd like to thank LSAM, funded by the NSF grant, for their support throughout the years. If you have any questions, feel free to ask. I'm sure both of us will learn something new.